And okay. Wait, maybe I should see if is it recording audio. How do I check once I started the recording?
You just press and hold on the thing. Press and hold.
Okay. All right. Welcome to the review day. So the way we're gonna do the class is the first 30 minutes of class we're gonna cover material, and then from there I want you guys to stop me at 9 a.m. and from there I will cover two things that I want to cover that are review, which I want to emphasize on, and then the rest of the thing I'll go over the tests and then open the floor to questions. Okay, and then of course this is all being recorded and will be uploaded tonight to the channel. Okay, which if you're listening, if you're seeing this in the channel, it's been uploaded. So last time we were talking about different kinds of binary trees. And we talked about 5 properties, and then we talked about a full binary tree, and then we talked about a complete binary tree, and then we ended the class talking about a perfect binary tree, which is basically a perfect binary tree of height h, where the height is the number of nodes on path from root to relief, has 2 to the h minus 1 nodes. Examples of perfect binary trees are ancestors and family, keep a person at a root, and parents as children, and parents of parents as their children. So that's where we ended class. And so I was going to start by talking about a balanced binary tree, which I have mentioned the term already last class, but we're going to properly define it. And then, even though I also mentioned we will properly define a degenerate tree. Okay, so what is a balanced binary tree? Well, the definition is a binary tree, and this is from Geeks for Geeks, so the book might have a slight variation on the definition, is balanced. A binary tree is balanced, or it's defined as to be balanced. I'm a little bit sick, so bear with me on the voice. I might be able to turn the microphone on if there was one. But yeah, a binary tree is balanced if height of the tree can be measured in log n, meaning that based on the number of items n, if you take the log n of that, that will give you the height. Now remember what the height actually is of a tree, right? So if we make a binary tree, this is level 0, 1, 2, and 3, and what's the height of the tree? Is it 4? Okay, so that's good that you guys are not sure about that, because it really depends on what you define as a height. If you consider a tree of nothing to be height 0, and then you consider a single node to be height 1, if that's the case, then if you're, then this would be height 2 like this, and then height 3 would be like this, and then yes, this would be height 4. If you're considering that way. Otherwise, which you frankly should, because otherwise, if you consider a single node to be height 0, then the empty tree is kind of weird, like it's a -1, or like, it gets weird. So yeah, I think I would say 4, but just be careful based on the definitions. But anyways, the point is, if you take the number of items and you take the log n of that, so for example, here we have this tree here that has 1, 2, 3, 4, 5, 6, 7, and maybe 8. So it's easy, log n. And so the log n of that, of course, we're using base 2, is just going to be 3. So is this a height tree? Well, it's a little bit off from that, but as you can see, I would still consider this to be a balanced tree, because in addition to saying that the tree is balanced based on just whether the height is log n, where n is the number of nodes, there can be variations on the definition based on the algorithm. So, for example, ABL trees. That's a category that we're going to spend some time on after the test. And for ABL trees, to maintain that log n height, we're going to make sure that the difference between heights of the left and right subtrees is 1. So what this is saying is, I want you to look at the tree backwards from the bottom up. So if I have the following tree, and I'm just looking from the bottom up, the first part that I can look at is this subtree right here. In this subtree, we can say that these guys are 0 in terms of height because they have no children. And then we can say that this guy has 1 height on the left subtree, which is this one, and 1 height on the right subtree, which is this one. From there, we can go ahead and look up here. This guy now has a height of 2 on the right subtree, that's right subtree. And then over here, you know, to be able to figure out, we start from the bottom. So we look at this one. This one has no children, so there's 0, 0. And then it has a height of 1. Now, because this here has a it's a difference of 1 either way, you can take the absolute value, you know, do some subtraction, take the absolute value for that. If that number is 1 or less, so 1 or 0, then you can consider this to be a balanced part of the tree. And now I don't want to say the entire tree is balanced because there might be more after that. But at least this part of the tree that we're looking at, this subtree, is considered balanced because a difference is 1 or less. If it's 2 or more, so for example, suppose that you did have a tree up here, but over here there was nothing. Or maybe they just, no nodes at all, like that. So then this has a difference of 0, and this has actually a 3 here, because from 2 to 1 more node up, it's a higher level. So even if this had a single node here, and this was 0, 0, and now this became 1, there's still a difference of more than 1. Then we don't consider this to be balanced. And if this isn't balanced, as you would see, this tree wouldn't be of height log n. Or log n height, and so it wouldn't be balanced. On the other hand, there's also an algorithm called RedBlack Trees, which we may or may not cover, depends. We only need to cover one of them, and I usually cover AVLs, but I'll try to fit it in if we have time. But yeah, so on the other hand, we have RedBlack Trees, and they maintain log n height by making sure that the number of black nodes on every root to leaf path are the same, and there are no adjacent red nodes. So what are these black nodes and red nodes? Well, basically, I would have to explain the algorithm, but in a sort of 5-second review of that is that you classify these nodes as red or black, and you sort of put 1 and 1, and it turns out that by doing this and trying to keep that sort of like checkered sort of system, then you can insert quicker, but it's not as balanced as an AVL tree, which it takes longer to insert, but it's more balanced. And by saying more balanced, I know it's kind of a weird term. I'm saying that typically the tree will be as, well, let's see which one we want to use. Perfect balance we want to use. It would be as full, maybe, as it can be. So, whereas technically, these two trees right here, I don't like that one too much. That's better. So let's move from here. We need to go ahead and do this over here. And then for that one more node, you can probably do it here. So let me check if this is balanced. So we look at 0, 0, 1, 0, 2, from 0 goes to 1. This is 3. Then this is 1. This is 0, 0, 1, 0, 2, 3. So this is a balanced tree right here. And on the other hand here, how many nodes we have? 2, 4, 6, 7. 2, 4, 6, 7. You could end up doing something probably like this. Yeah, I think this would work. So this would be okay with a RedBlack tree, but it would not be okay, I think, with the AVL tree. And as you can see, it looks less balanced. Let's see if this would be okay. So this would be 2, 1. Oh, that might not be okay. Let's see. So this is 0, 0, 1, 0. No, it is okay. So actually, that would also be probably okay for an ABL tree. So ultimately, it's kind of hard. So once we actually go over the algorithms, I can show you a concrete example. But ultimately, ABL trees are a little bit better because they are more balanced, but it takes longer to insert stuff. RedBlack trees, faster to insert, but not as balanced. That's just a quick summary of that. In general, why do we care about balanced binary search trees? Well, because as long as we can guarantee that they're balanced, and it says of the height being log n, then we can also guarantee that they will provide O log n time for insertion, searching, and deletion. And that's powerful because think back at arrays. With arrays, if it's a sorted array, you can use binary search on that sorted array to be able to have insertions, to have searching, potentially. What's up?
So on the left side, like that left there with 1, 2, how come it stays at 2? The left tree.
Oh, shoot, that's right. This should be a 3 right here. Okay. But it's still balanced.
Okay, yeah.
But yes, yeah, good catch. Yeah, so whenever you go up a level, I guess I didn't say this, but I should say more explicitly. Whenever you go up a level, you take the highest number of the 2 and you increase it plus 1. So because 2 is bigger than 1, I take the 2 and increase it plus 1. Over here, for example, there's a 0 and a 1, so I take the 1. Over here, if I had a higher node that went either direction, it would be 3 plus 1, not 2 plus 1. So yes, good catch on that. However, it's still balanced.
Yeah, I'm not saying it's not.
Yeah, no, but I'm glad you pointed that out. So yeah, back to this with an array. If you have a sorted array and you use binary search, you can achieve log n time for searching. Deletions, if you just mark things as deleted, you can kind of get away with it. But the problem is going to be that it's going to lose efficiency the next time that you try to delete something because now there's empty spots and it's a mess. Same with insertion. With insertion, you're going to have to resize it, and now we're talking it's going to take n time. So that kind of, is inefficient. If we look at the linked list version of this, and of course vectors is the same thing in reality. I mean, yeah, they're nice, but ultimately they're still arrays. With the linked list, you can insert, no problem, if it's unsorted quickly, but if we're looking at sorted data, you can't use binary search on a linked list. So you kind of lose that log n time to insert. You can delete and put things in quickly, but finding where to put them is the slow part, and that's going to take n time. So that's also out of the picture. Binary trees, however, allow you to do both insert, searching, and delete in log n time. So this is at this point of this class, this is the best algorithm that you've learned to store data that is sorted. Of course, hand-waving the part that we don't know how to balance them yet, but we will when we talk about ABLs. So that's why trees and binary trees specifically are such a huge deal in data structures, because they can make us achieve this log n time. So anyways, we will definitely talk more about balanced binary trees when we get to ABLs. But before that, one more term, and that's degenerate tree. If you really don't like the degenerate word, there's also the pathological, yeah, which is also the same thing. It's in interchangeable terms. I don't know why I memorized degenerate, but I guess that's just a popular one. Pathological sounds like it has a disease. Isn't pathology like disease stuff?
I think it's related.
Yeah, or I don't know.
We're not meds.
Yeah, we're not meds. I mean, I'm a doctor, but not that kind of doctor. Yeah, so.
Is there a doctor on the plane?
What's the Star Trek thing? Damn it, Jim, I'm a doctor, not a real doctor. I guess in this case, I don't know. But anyways, so the proper definition, let me just write it here. A tree where every internal node has one child. Remember, the internal nodes are like this guy not the leaf nodes. That's the other kind of node that you could have. And then such trees are performance-wise the same as linked list. So that's just a more formal definition to what I already talked about. Like I said, that's when does that happen? If you're just inserting up into a binary search tree data and you're inserting it in a sorted manner, like ascending or descending, it's going to end up either in this, like in this direction or in this direction. But ultimately, useless to us because we lose that login height and therefore it becomes end search time. So basically, we will be doing AVL trees to fight the degenerate trees and eliminate them from our code. Okay, so 15 minutes left. Cool. So that kind of concludes the introduction into trees, and now we're going to start talking about some applications of trees, I suppose. And the first one that I have here, I guess I could call. Sure, why not? This is just a definition, I suppose. But okay, why not? I have it here, so I'll list it. There's lowest. I think this pen is dying. The tip is dying. So I have another one, so it's good. So the first sort of mini use case that we're going to talk about is the lowest common ancestor in a binary search tree. So given two values, which we can consider like node 1 and node 2, or n1 and n2, in a binary search tree, the lowest common ancestor is going to be just kind of what the name implies. So here's an example of a tree. I think just showing this by example will make so much more sense. Remember, anything on the left side of 20 has to be less than 20. It doesn't matter how low you go on the tree on the tree structure here. That's why 14 is on this side, but 22 is on this side. Because 14 is to the right of 12, but it's technically to the left of 20. Okay? So now that I have this tree, the way that I can do the lowest common ancestor is I can list two nodes, n1 and n2. So for example, lowest common ancestor of 10 and 12. Or sorry, not, well, they're spelling. And 14, which I already wrote the answer, is 12. So what it means is like, think of a family tree and like, what's the closest related kin that they have. So like, if you're cousins with someone on like the mother's side, then your grandmother's the lowest common ancestor, right? Because I mean, technically your mom and your aunt are related, but they're not both your parents directly. The grandmother is the one that's like the DNA is coming from, right? And technically your great grandmother or great grandfather on that side, they're also the same DNA, right? But the split happened at the grandmother because that's when your DNA got split from theirs because they procreated and created kids, whatever. I don't know. But anyways, so in this case, 12 will be the common ancestor because that's where the split happens. Technically, 8 is also an ancestor of both 10 and 14, I suppose. But again, we look at the closest one.
That's the question?
Yeah.
If 4 had 2 ancestors, or 2 children, would 8 be the common ancestor then?
If 4 had 2 children?
Yeah.
Well, if for example, 1 and 5. The common ancestor of 1 and 5 is just 4.
With the lowest common, would you have to take it amongst all 4 children?
Well, okay. Suppose you said what's the common ancestor of 4 and 14. Then it would be 8.
Right?
Is that like your case? Which case? I mean, pick two numbers and tell me which.
Well, no, I'm just wondering if when you say lowest common ancestor, if that applies to the state of the whole tree or just like one part of the tree?
The entire tree, but only where the two nodes connect for the first time. So, for example, another typical case that you will see is like the lowest common ancestor of like, so let's say 14 and 8. Or 14 and 8. It's not 12. It would be just 8 itself.
Right.
That's like saying between your grandmother and your grandchild,
Right.
the common ancestor is just the grandmother
So there's
itself.
like some kind of scope between it that you're talking about.
I suppose you could think of it that way. And you always go up. You don't go down.
Okay.
For example, the lowest common ancestor of 10 and 22. 20. Yep. And then
you
like
say the lowest common ancestor of 1, 5, 10, and 14 is 8?
1, 5, 10, and 14 is 8. Yes.
Okay.
Yep. Good. Yeah. Here, I'll even write it. Cause I don't know if they can hear you in the recording. 5, 10, 14 is 8. Because they flow, and they meet. And there you go. So that's pretty much all there's to it on that. On understanding what that is. And so how do you actually find this algorithmically? You can recursively traverse from the tree from the root, get to the nodes that you're looking for, and then go backwards, and which means go out of the recursion and see when the two things basically meet up, and that's when you can detect it. So there's some code online, and since there's no assignment on this, you can just look at it on your own time. It's just one use case that is typically used a lot. I mean, it won't show up on the homework. It might show up in the test, but it won't go any deeper than this. So. But yeah, okay. Any quick questions on this? So I have traversals. Yeah, we can try to do traversals. Okay. So this is where your assignment 6 is going to come from. Okay. So when you have a tree, for example, let me put this tree here. 1, 2, 3, 4, and 5. You don't necessarily have to make it a binary search tree. It can be any data, okay? So now we're gonna kind of switch a little bit of gears and remove the search part and just make it into a binary tree, okay? Because making it a binary search tree and making it so it's sorted like that, that's one thing. But you don't have to do that. Think back on what I first mentioned trees, and I was talking about file hierarchy. You don't have to sort your files. You can. Your root directory doesn't have to have a folder on the left side that is like less than R and a folder on the right that's greater than R. No, you can have a folder called CS302 and a folder called CS202 and call it a day. And in those, you can have a folder called Z and mess that order. It doesn't matter because, again, it's hierarchy based. You don't have to make it sorted. So here's an example of just a tree. Of course, it's not binary search anymore because, as you can see, the 5 breaks that rule and so does the 4. But that's okay. That's perfectly fine. Okay, so given this tree, it's very easy for me to just draw the tree on paper and be like, that's my tree. You can see it. You can see that 2 has 2 children, 4 and 5. You can see that the lowest common ancestor between 4 and 3 is 1 because you're drawing it and whatnot. And that's all great and awesome. But can you just draw something in a computer? I mean, well, you could code a really nice UI to do it, but typically, you can't. You have to represent it in some form of array where you can keep the numbers, or a linked list, or some sort of data, right? So traversals is a way of listing the numbers in an order that is going to depend on the traversal it is, And then eventually what we're going to do is we're going to take 2 traversals, and out of those, recreate the tree from that. Because even in the sorted binary tree, if I have the following 3 numbers in my sorted binary tree, I could have that 3. I could also have that 3 and one more. Can you guys think of what that one more is? Which would be the root node? 3. Oh, that killed it. And then 2. And then 1. And could I have another one? I don't think so, right? Anybody think of another case? I mean, you could do the permutation thing in math and figure out that. I think that's it. No. I found another one. And then that means that I can have another case then too. I think I can do the same thing on the other side. So I can do 2. I might have run out of options here. 3. 1. No.
Branch it off to 3.
Branch it off to 3.
2.
3.
No, 2.
3, 1, 2. I did that already.
2, 3, 1.
2.
3. No.
I can't do that. This will not work, man.
Continue down.
Okay, what is the root? What's the root?
Root is 2.
2.
Down.
Root is 1. That sounds much smarter, actually. I'm gonna go with that. With the 1. There we go. There we go. I knew that it had to be a mirror of this one.
You're still missing one.
Okay, what's the one that I'm missing according to you? What's the root?
2.
And then, okay, what is my left child?
You'll have one child.
Okay,
Yeah.
is
3.
which one? The right one?
Doesn't matter. 3.
Okay.
And then 1.
Well, 1 can only go here
Why?
because it's binary search. That's what I'm saying.
But didn't you make us go left? 3, 2, 1.
Oh,
Wait a minute. Wait a minute. What?
no, these are all perfectly fine.
What
Yeah.
What is that bottom?
Which one?
The middle right one. Where you go 3, 2, 1.
That's okay. That's perfectly legal.
Wait. Then why isn't what I said legal?
Because it's not. I mean,
Wait.
I think this is it, right? I think this should be only 5.
But that's not a permutation of 3.
No. What you wrote, the problem with what you wrote is this. You said to put 2, 3, but the problem is that 1 can only go to the left of 2. So you have no choice but to put it there.
Oh, you have to keep it with it.
Did I already do this one, by the way? Oh, I didn't do that one. No, but that's not right. That's not right because it's a 3. So I think this is it. Assignment 8. Create a program that can do this for me. No? Okay.
Wait, but then why do you jump from 1 to 3 then?
Where? Which one?
And you do 3 to 1?
This one? This one? You don't understand?
3 is bigger than 1, so 2 is less than 3.
Yeah.
So bigger than 1.
Yep.
So
Believe me, man. Believe.
Oh, okay.
Got to believe. All right. Just remember the rule in the binary search tree that the child has to be less than on the left side and greater than on the right. 3 is greater than that, so we're okay on that. And then 2 has to be less than this, greater than this guy, but less than this guy, so it goes here, so that's okay. So anyways, that's, is it permutation or combination? Permutation? Permutation, yeah. 351. Okay. So anyways, don't get confused because this is not a search tree, this is. My point is that, as you can see, me just listing the items in this format is not enough to define what the tree actually looks like. So traversals are going to help us avoid this sort of ambiguity. There's 4 traversals that we're going to talk about, or we will in the future because we're running out of time. There's in-order traversal, there's pre-order traversal, there's post-order traversal, and then there is level order traversal or breadth first search. Breadth first search. Remember breadth first search? It's back.
Didn't you call it depth first search? Oh, yeah, it's back. Didn't you call
What?
it-
Hold on, what?
You said it's 9. You said it was 9. It is 9 o'clock. It is 9.
Oh, it is 9. Yeah, I know. That's why I said I will talk about it next time. Yes. Thank you. But yeah. So
Question was depth first search. You know?
what's that? Oh no, we did depth first search. That's right.
Yeah.
And technically, these are sort of depth first in a way. But we will talk more about depth first and breadth first actually later on. But yeah, these are the ones that we will be talking about next class. Okay. So we'll pick up from there. Okay. Next topic, now that it's 9, is going to be the review of 2 subjects that I have talked about, but I don't think I emphasized enough, and that's why I want to re-emphasize, because they will be on the test, and so I want to make sure you guys understand. So I think, yeah, it's still recording, so. Okay, and I created 2 pages on Canvas to support this. So, the first one is the comparison between Quicksort and Mergesort. And this is a table that I took from Geeks for Geeks. And it's just a nice little summary that you can use to sort of refresh. And I wanted to kind of go over that as the first review item. The first one is, what is the worst time case complexity for Quicksort? N squared, that's right. It's not n log n. So technically you could say that Mergesort is a little bit better because it doesn't matter what data you throw at it, you can guarantee that it's not ever going to be n squared. It's always going to be n log n. However, in real application, there are cases when you want to use Quicksort and there are cases when you want to use Mergesort. And so this table is supposed to kind of help you understand that. I think one of the most important ones is going to be whether the algorithm is stable or not. So remember, stability has to do when you got duplicate keys, if they're going to get swapped around. And so Mergesort is stable. I can't really highlight, can I? Maybe I can. Well, there's that. So we're looking at that there. So, Mergesort is stable, Quicksort is not stable, and that has to do because of the pivot swapping stuff. And that kind of also bleeds into the fact whether it is in place or not in place. So Quicksort is done in place, meaning that you don't need an extra array. You do it in the same array where the data is stored in. You just have one temporary variable and then you swap things around, either of the 2 methods, whether it's Lamudo or Horse method. And then Mergesort, on the other hand, you create a brand new array when you're merging back together. And so that requires n extra space. So your auxiliary space is going to be O of n in Mergesort versus O of 1 in Quicksort. And those 2 things, the stability and the fact that you have the auxiliary space, kind of have a play between each other. As you can see, Quicksort is better on a smaller array. But Mergesort, the real power of that is that you don't need to have the full data even on memory to do Mergesort, and that's Polyphase Mergesort, and it's useful when you're sorting like insanely huge amounts of data that you wouldn't even be able to think about fitting in main memory, and you don't want to have you don't want to read and write to a hard drive because it's super slow. So suppose you have this big file that's like 2 exabytes or something. And so you're sorting this, right? And you end up splitting it. And then for the last step, you have to merge probably 2 1 exabyte files, right? Because this is going to get split first into like 1 exabyte. It's exabyte, right? And then from there it goes to terabyte. I think 1 exabyte is 1,000 terabytes, right?
No, 1,000 petabytes.
Petabytes.
Yeah.
Yes, exabytes is like a million.
Oh shoot. Yeah, that's big right there. Though. Let's stick with the petabytes. Then. I remember when terabytes was a big thing. In Terminator 3, they said like Skynet was running at 9 teraflops per second, and that's nothing now. So sad. Anyways, but okay, so these are 1 peta. Well, now that we're at the ones, we can say this is 1,000 terabytes. That's a 1, not a T. And then from there, this gets split into 500 terabytes, not gigabytes. Yeah, this is really big. And so on. So ultimately, when you get to the size where you can actually fit it in memory, maybe you can run Quicksort on that actually. But the point is that even with like a nice computer that has a terabyte of RAM, which is like what we have in GPU, if you're merging a 2 terabyte file, you can't fit that in main memory, right? So let's say you get to the level where you have a 2 terabyte file. And so you're merging 2 1 terabyte sublists. So what you do is instead of just loading the both in memory, which wouldn't fit, you just load a part of the file. You load the beginning of the file. Because remember how merge sort works. With merge sort, you have 2 lists that are sorted on its own. Maybe you have here a 5, well, no problem, 40. And then 1, 1, 1, okay? And it makes it more exciting like that. So when you're doing merge sort, you start out by having just a pointer to the first item of each list, and then you get the smallest one into your brand new list that you're making, and you put it there, and then you move the pointer, and then you commit to going with the left side first, and then the right side. That way you keep the stability, and then you get to 3, goes to 10, then you get the 5, this goes to 40, and so then basically you get 10 and 11, 10, 11, and then 40, and then 1, 1, 1. Okay? So here's the thing. If I couldn't fit these many numbers in memory, I could load the first 3 numbers, and then when I finish them, I could load the next 3 numbers, and so on. And the same thing can be done here. So I can load the first part of the list, and as I get closer to the end of that section I loaded, then I can load the next part. And I don't need to have this part loaded anymore. And also, for the writing file, I don't need to have the output file loaded in memory completely. I can write directly to a file as I'm merging them and not have to have it in memory. So that allows me to be able to merge this list quickly without being slowed down as much by the hardware read times versus like RAM. Okay? So that is Polyphase Mergesort. And another great thing about it is that merge sort is easily, embarrassingly parallelizable. So you can make it parallel very easily because each of these 1 terabyte files, the way that we made them, for example, they can be run in different machines. And then I can just split this huge file into multiple computers and then just run like MapReduce on each one and get the thing done. So, anyways, locality of reference, they'll talk about that in 219 with cache and things like that. But that is one sort of disadvantage of Mergesort, I suppose. That's actually considerate. But yeah, so even so, as you saw, Tim's sort is going to be faster. But I just wanted to kind of bring that up. And then the other thing that I wanted to sort of re-emphasize on is, I think I talked about it, but I talked about it very briefly, is the lower bound of comparison-based sorting. So let's think back at what big O means. I've said that big O means the worst case, and I stick to that definition. However, that doesn't mean that it always signifies an upper bound or lower bound. It's talking about the worst case of maybe the upper bound or the worst case of the lower bound. So when you typically think of big O, like for example, Quicksort and squared, we're saying that the upper bound of that in the worst case is n squared. But I could also say that the lower bound of Quicksort in the worst case is going to be like n log n. What that's saying when you're talking about lower bound is I'm saying even when my algorithm has the best possible use scenario, what can it achieve, but still using the worst possible data? So like I could have a really worst possible data, but the algorithm can handle good. But it's still the worst case because it's the worst case of data for the lower bound. So ultimately, you can talk about big O in terms of lower bound, just like you could I suppose talk about omega in upper bound, I suppose. I mean that'd be kind of weird, but that's like saying given the best kind of data that you could have to try to achieve the slowest runtime, which would be kind of weird. So it's weird, but I mean you could technically talk about it that way. But makes more sense when you're talking about big O in terms of lower bound. So the best example of that is when we want to define the lower bound of comparison-based sorting. So this is like a very, very baby proof here. And so if you think about how comparison-based sorting works, each comparison ends up in a yes or no, which is swap or not swap, basically. And so when you're comparing things, you got to think about all the possible combinations that you can have of input that could result in swap or no swaps. And so we were just talking about permutations a minute ago, and it actually turns out that it's going to be n factorial permutations for a data of size n, which is all the basically orderings of the data. So if we have 10 items in the data, how many ways can we order them? And so in that list, we're going to have the best case scenario for the algorithm. We're also going to have the worst case scenario for different places. And so the one we really care about is the worst case scenario. And then we can apply that in the upper bound and lower bound. And so here, as it's saying, and when you have n factorial permutations and you're using yes or no decisions, that's base 2, so that's your log of n factorial. And so that is going to be basically the number of comparisons that you need to have in the worst possible case. And so you can go ahead and sort of rewrite that as saying n factorial is greater than or equal to n divided by 2 to the n divided by 2. And if you take the log of that, then you can do the trick I showed you like long time ago, where it is to take the exponent and bring it down to multiply. And so now it just becomes a constant, the n divided by 2 times n. And so you end up basically with n log n. So what this is saying is that mathematically, these people can prove that you cannot do a better sorting algorithm that in the worst that can achieve better than n log n time in the lower bound, given any kind of data you throw it in. So merge sort can do n log n. That means that actually merge sort is probably the best that we can do. At that point, we're talking constants. The constant can make it like, yeah, this can run half the time of that, but it's still a constant. But we're saying, removing those constants, you cannot do better than n log n. So if you're thinking like, wow, I can come up with an algorithm that can sort it in time, the math people will laugh at you and show you this, basically. So this is strictly for comparison-based sorting, though. There's another kind of sorting that's like, for example, bucket sort and radix sort. And so those are not comparison-based, and there's always a catch to them. For example, and we might touch them at some point, but they're not really that important or relevant. But like, for example, I think it's bucket sort, where what ends up happening is the way you sort it is you look at the number, and each digit of the number you're going to sort of store in that index of an array. And so you have different buckets, basically. So like here, instead of hand waving, I think it's better to just do this fast. So if we have, here's the first catch. They all have to be a certain size. They can't get too big. So suppose you have those numbers. What you do is you store them on little buckets. So you look at that, and you have 10 buckets from 0 to 9. And so you have 2 here, and then you have 5 somewhere here, right? And you have other numbers here. So in here you're going to store 2, 3, 4, 2, 2, 3, and here you're going to store 5, 5, 5, and 5, 5, 6. And then in here you're going to store 108. And that's it, right? Are we missing one number? No. 1, 2, 3, 4, 5. Yeah. And so you could do the same thing for the second digit and store them in sub buckets too. And so you could achieve something like this in less than log n time. Oh, sorry, less than n log n time. You could achieve it in n time. The catch is, because these are immediate, because this is like inserting into an array, so that's O of 1 time to do the insert. But the thing is, yeah, sure, you can say you're doing it like n time, but you got to do it for each number of bits here. So it actually is more like n times m, which is kind of like n squares. So they're not that good. There's always a catch to these algorithms. So don't think that like you don't get sold snake oil basically. So like I said, we might talk about them someday. Maybe like a study week or something if we're bored. So anyways, my biggest thing is that I want you to just understand and review that big O doesn't have to strictly mean upper bound. It can mean lower bound too. It's more talking about the worst possible data that you feed it in that case. And whether you're referring to that as upper or lower bound is up to you. Okay? And the same can be said about omega and theta, by the way. Okay, so now that's the one thing that I really wanted to review, because that lower bound stuff will be on the test, and big O as well. So other than that, before I show you the test, does anybody have any questions that you want me to go over, like any topics quickly? Yes.
Can you kind of go over current relations again, like how?
Well, I can kind of give you a quick guide, because I can't really go through an entire example. But what I can go over is the following. There's 3 methods that we talked about for solving them. In one of the methods, we start at the base case, and we work our way towards the end case, T of n. In the other method, we start at the end case, and we work our way to our base case. So work towards base case. And here we're working towards the end case, from the base case. This method here is the one that we did, I think the first day that we covered recurrence relations. That's the one where like, we basically write out each term in respect to the previous term and so on. And then eventually we try to cancel out terms, and we ended up with something like T of n minus T of 0 or something like that equals to 2. And so that method is useful for very simple stuff. But other than that, it's usually not that great. This one is the build and expand method. And because we're working from this to the base case, typically like something happens to the n from here to the next case. So maybe it gets divided by 2, gets multiplied, something happens. And hopefully it's something that is increasing the size of it. And so what we're doing is we're trying to find a pattern and seeing at what rate it's decreasing, and create a pattern to that, which is like a general case solution with i's, and then solve how many times we got to repeat that to get our base case. And then we solve for that, we plug that in, and then using that plugging in, we come up with the solution. And then finally, I showed you also the master theorem, which can also apply for a lot of the cases, as long as your a, b, and your function fit certain parameters, such as like, I think a has to be greater than 1, b has to be greater than equal to 0. You know, it might be the other way around.
That only describes theta.
And d, which has to be function as a function here, has to be also greater than 0. What's that?
But that only describes theta.
Yes, that's the other thing. The master theorem is going to give you sort of a general solution per se, but not the exact solution. So that's, this is kind of your theta. It's bound, but it's not as bound as this, which will give you the upper limit. So this will give you right at the top what the exact number is.
So when
Which-
you ask for exact solution, we are using the first or second one.
Yes, otherwise you risk not being exact, potentially.
So are you allowed to call theta like the average case?
No, technically not.
So,
Technically, that's like it's used all over the internet, but technically it's incorrect. Because average is a math term, it's mean, and it's computed by adding everything together and dividing it by the number of items. And this is not using that. So,
how should we describe it?
well, the way you describe theta is you say that there exists a constant k1 and a constant k2, and given these constants, you can you can define a function that will be in between big O, that will belong to big O and big omega. That's the formal definition that I wrote. there's math definitions that you can write, by the way, for big O and theta and big omega and theta. Well, theta I told you, but big O and big omega, where it's like the function f of x belongs to. I don't remember that off the top of my head. Here I have it. So, for example, this is remember the thing that I wrote where like I said like, you know, you got gxx times k for some k. And then f belongs to OG if and only if there exists an n for all x greater than n. I like how I just had this like ready to go. F of k less than or equal to j. So you can also put that on the test, and I mean, that's more accurate than anything. You can write it by words. So yeah, so you should have those in your notes. But yes, don't ever say theta is average, because technically it's wrong. What's that?
That's your mathematical definition.
No, this is actually big O. For theta, you have to have K1 and K2 because you have both omega and big O.
Would a good way of describing theta in Langford's terms be not the average case, but the typical case?
Yeah, I would prefer the word typical because it's less technical, so it's okay. If less technical is better in this case. The moment you throw math terms, then math people get mad at us. With a reason, you know, it's fair. So, yeah.
How would you efficiently show the quicksort algorithm for a list of 16 numbers, like on your worksheet?
Oh yeah, so I told you in the class, I never actually like tested how many times you'd have to do that. So I didn't know.
How long is our list on the
So
because that takes like a whole entire
yeah. So don't worry. The test version of that is a carefully curated list with 8 numbers.
8 numbers.
Yes.
Is that the same for
And it's carefully curated because you don't have to do that many. So like I want to make sure like there's like empty pivots, you know, like where you have one side is empty and the other one is full. And there's also cases where like things get split nicely, like you have to swap. Like I created this specific example to make sure that it only covered what it had to, and you didn't do like the same thing 5 times. And then
is it the same for Mergesort, like with a list of 8 or
yes,
okay.
I use the same list for both actually. So it was kind of tricky. Mergesort wasn't that tricky to come up with something that applied. Yeah, but yeah.
Could
So
you demonstrate how you would want the answer to be related though? Like,
yeah, sure. So
for Orr's method.
horse method. Okay. So what you do is you have that, and then you select your pivot, and then so what you want to do is you want to show every time you do a swap. So for example, you know, you have your low and high, so L and H, whatever, and then L is less than 2. This is greater than that. This is bigger, and this is smaller. So the next time I would write this like, oh no, my bad. Yeah. So in that case, then you would just swap the 2, 4, 5, 8. So they would show that, and then you would basically be like, okay, that's done. And then you would say something like Quicksort on 0, 1, and over here you would do Quicksort on 3, 0, 1, 2, 3, 4, 3, 4. And then you would basically say this is your pivot, 2, 4, 5, 8.
Where do you get 3 and 4 from?
Indices,
Oh, indices, okay.
right? So I mean, if you want to number them, you probably should. So make sure I don't mess up. So 0, 1, and 3, 4. Yeah, okay. So then in this case, nothing happens. So then you can just say you do a check mark, and you can even write an arrow saying, okay, now I'm going to do this part.
Would it be 0 to 0? Yeah, because we don't use the pivot since it's already sorted. The pivot moves and it's already sorted.
I know, but I didn't use the pivot. Pivot is 2.
Yeah. No, it's 1. It's Quicksort 1.
Oh, that's right. I thought I put a 4 there, but it's 2. That's right. Yeah. I didn't see that. I thought I swapped it with the 4. So, okay. And then this one's actually 2 then. That's actually better because it's better, more code. So then, okay, so this one you can say, you don't need to write that actually. You know, I mean, you can write it and then say like it doesn't get called or something. Doesn't call it single digit or something, single number. So then, so now you're looking at this guy. So 4, 5, and 8, and you can, if you want to feel better, you can draw a line to not get confused or draw a box, whatever. Circle your pivot and then do the same thing again. So in this case, nothing's really going to happen other than the 5 and the 8 swapping. So you can do that. And then technically, you're going to call Quicksort.
Wait, why would they 5 and 8 swap?
Oh yeah, they shouldn't swap actually. My bad. So technically, low plus 1. So technically, swap 8 with 8. Yeah. I mean, I'm trying to do this fast. That's why you guys have more time. So you call it on that, and then nothing happens. So I think at that point I would be okay with that. Okay? So just show each swap, basically. And then explain a little bit about how pivot happens and how you swap.
Do we have to use both methods of Quicksort?
The question will ask you for one of the two methods.
Or we can choose? Or
Well, no, if it asks you for one of the two methods, then you gotta use that method. It'll say like use core methods for this list, and then use Lamuta's method for this list, that kind of thing. So yeah.
Is there one for sure about merge sort where we have to like do merge sort on a linked list? I mean on an array?
No. It's gonna be the array version. Always do the array version for that. Do not do the linked list version because you not never do that really in the real world. However, for the merge sort, it'll be the opposite. For the merge sort, you can just do the big tree where things get split and put together. That's perfectly fine because that's really how you do it. Quicksort is the one that I want you to do in place. But merge sort, you can do like show a tree and you're good to go. Yeah, you asked I saw a hand.
Could you show us an example of a merge sort, please? Like,
Well, okay, I can, or I can show you the test.
I mean, like,
I'll do it for 4 numbers. How about that? 5 numbers. So 1, 2, 4, 5. Well, let's not do it on the sorted one. Like that. So then this gets split up into 4, 2, 1, 3. 4, 2, 1, 3. 2, 4, 1, 3. And then 1, 2, 3, 4.
And that's perfectly acceptable work.
Yes. I mean, you got to explain a little bit here because the question asks to explain how Mercer works. So you would say you split it into sub list, and then when you get to a single unit level, combine them one at a time, and so on.
so the other question I had is, what if the list was an odd number instead of even?
Well, then there's part of the algorithm says that you got to decide that in a way. So what you do is you basically have to pick left or right, 1 plus extra.
All right.
So okay, so now let me switch to showing you the test.
Solution man, right?
Yeah.
You're showing it's a solution man, yes.
Yeah.
These exams are always like this. You don't play no games.
All right. So that's the test right there. That's actually the solutions right there. So what I'm going to do is I'm going to go over each question, and we have 15 minutes, and then I'll just tell you what the topic is and what you should focus on. And then you can see the point distribution there. The test is out of 3,500 points. It's okay. You can take, if it makes you feel better, take the last 0 out of everything and make it out of 350. But then I have, questions that are worth 4 points and 7 points. And that's weird to get partial credit. Okay, so I really worked to try to bring the test size down because I started out with the goal of going for the 15 questions.
Did you?
And then it ended up being 25 questions. And then I brought it back down to 21 questions. And then I added 3 review questions of 202, and that's how we got to the final test. So, yeah.
I thought you said there was going to be like 8 questions.
I said 15, but then things changed once the test was actually created. So, okay. So questions 1, 2, and 3 are C++ review. They are questions that if you've done the assignments, you should be able to answer. The first one's super easy. You should just get it done. It's literally 2-word answer. Question 3 is relatively simple. People in 135 could do that. People who do actually questions 1 and 3 in 135. So if you get that wrong, you should feel ashamed. Question 2, however, is a little bit trickier. But if you remember your 202 and if you've been doing the assignments and if you remember virtuals, then you should be good. So I'll leave it at that. And it's only worth 70 points, so it's only like math. Just whatever 7 divided by 350 is. That's your percent. What is that? %. Yeah. If you do the extra credit, it means nothing. So, okay. Anyway, I got question 4. We gotta keep going because otherwise we're going through this. That one is going to be like the worksheet where you have to remember question 1 in the worksheet 1 where you had like a bunch of different time complexities and you have to sort them out by grow rate. Same question, different numbers. Question 5. That's the big one where you gotta explain big O, big omega, and big theta with your definitions and things like that. So make sure you know it. Question 6 and question 7 are both algorithm analysis kind of questions. More about big O and big theta, and it's about like, what can I tell you about that? Just understanding them, really. This will tell me that you actually understand the definitions that you just gave versus like just regurgitating information. So yeah, that's a good thing. Question 8 is a multi-part question. It's 5 pieces of code that, like the worksheet, where you looked at the code and got the time complexity. So like you looked at the loops, like nested loops was n squared, that kind of thing. Just like the assignment, there was a thing where like one of the codes called a function that was in the other code. So it'll be the same thing. The catch here being that, not catch, this is good for you. If you mess up, for example, I'm looking at this here and like code snippet 4 calls code snippet 2 function. And so like if you mess up the time complexity of code snippet 2, you lose points for that. But then I'll take that wrong time complexity figure out, and if you apply correctly for code snippet 4, then you'll get points for that.
Oh, so you're generous.
Yes.
All of those.
At least that's what I told the TAs. Hopefully they. If when you get the test back and we go over it, they don't do that right, then we can correct the grade.
For that question, can we just analyze the code and write down the time complexity?
Yeah, you don't have to do the recurrence relation for that. No, we'll get that. We'll get there. We'll burn that bridge when we get there. So, okay. Question 9 is going to be like the worksheet again. So the worksheet, there was a 2-part question in the worksheet that asked you like 2, or actually technically 3 time complexities. Remember? Like it was like inserting an item into a linked list or something, and then the third one was like the joke, difficult to get an A in the class.
Constant.
Yeah. So yeah. So here you have A through H of those, and each of them you have to not just list the time, but also list any sort of assumptions you're making, right? Because they could vary. If you pick the best case scenario, then you don't technically have to do that. But if you don't, and you're technically wrong unless you explain why that would be the case. Like for example, if you tell me inserting at the back of a linked list, unsorted, is O of n, I'm gonna be like, no, it's technically O of 1 if you have a tail pointer. But then you can be like, well, assuming I don't have a tail pointer, that kind of thing. There is one mistake in the question, which I want to point out, because I won't be here. It's not technically a mistake, but here's what ended up happening in that question. So I did the test in LaTeX, and it's kind of tricky to do that. So like the question at the end says like, blah, 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 justify your answers and list your assumptions. And this is all in one line. And then it says period A like that. And then the next one it says like, this is not the one that is here, but it says like, insert a node into a binary search tree, for example. This is not what's in the test, of course. And then there's like B is here, and then C is here.
Are you showing us all right now?
Ah, good point. So this is question 9. So it has like all the prompt, and at the end of the prompt there's a period, and then there's an A, and then there's this thing, and then there's a line here that says insert a node into a binary search tree. It's not binary search tree. There's no binary search trees in the test, because that's test 2. But I'm just saying, imagine it's something like that. And then the second one says like inserting a node into a binary search tree again or something, right? This should have been like entered here, line feeded, you know? So it kind of bleeds in with the first one. So if you read the full question fully, you'd notice that. But if you don't, and you just jump in, you might miss that, okay? So make sure you don't miss that. And you see like it starts counting from B. And it's not, because technically it's A is there, okay? I'm just saying, do not miss that. Does that make sense?
Yes.
Okay.
There's instructions that
Please
should be
catch
up
that you're
top,
starting on
but
Basically, I forgot an enter line. I forgot to press enter. But it's latex, so you just don't press enter. You gotta put 2 slashes.
LaTeX.
Yeah. Okay. So I'll tell the TA to remind you that once you actually have the test in front of you, it'll make sense. But, you know, I don't know if the TA will remind you. So that's why I'm telling you. Okay. Back to this, so you can see the point distribution. Questions 10 and 11 are stack and queue stuff. That's all I'm saying about that. Question 12 has to do with what we were just talking about in class with the bounds, like sorting bounds and things like that. Bounds. Yeah, like upper bound and lower bound of sorting and that kind of thing. Questions 13 and 14 are sorting analysis. So that's kind of like the comparison of Quicksort and Mergesort, like looking at stability, in-place stuff, space, that kind of thing. Yes. Question 15, I told you would be on the test, and it is on the test, and that's a chart. You got to fill in with all the time complexities for all the sorting algorithms we talked about. So Quicksort, Mergesort, selection sort, insertion sort, and bubble sort. And there's big O, theta, omega, and space complexity in terms of auxiliary space. So that's going to be, what is it, like 20 things that you got to put in there?
Isn't that the worksheet question?
Yeah, isn't it like the
Yeah,
one, two?
yeah.
Is it exactly like the worksheet?
Yeah.
Was there 5 there on the worksheet?
Yeah.
Well, there you go. I don't know if they're in the same order, so I wouldn't just like memorize them. But
Like this, right? That one, right?
yeah, there you go. You just talk to the TA to make sure you got it right. Okay. Question 16 is the part where I know whether you memorized or you understood. So it talks about the worksheet, and then you got to explain some stuff about it. So that's where I understand. If you know, 'cause I mean, anybody can memorize things, but do you really understand what that means? You know, do you really understand what auxiliary space means? That kind of thing.
Wait, so 16 what? Worksheet. Explain something.
Some analysis on the chart that you just wrote from memory. So no, I don't like to just ask rote memorizing questions. I like to then ask questions that will follow up on that to understand if you really understand. So yeah.
So kind of like sub-questions.
No, it's not a sub question because it's its own independent question. But it's a follow-up question. That's a better way. Okay, questions 17, 18, and 19 are more of those kind of questions. So analysis on the chart. Question 20 is your quicksort question, just like the worksheet, but 8 numbers, carefully curated. But you still get like 3 pages of space in case you need it. Merge sort is going to be question 21, so same thing as the worksheet, just merge sort in this case. And remember, like I can read it out loud. Explain to me how the quicksort algorithm works. Make sure to include an explanation of how to pick the pivot and how the partitioning works. Include cases of when the algorithm performs poorly and why. Along with your explanation, sort the following numbers using quicksort. So there you go.
We don't have a choice in what we choose as the pivot, so it's not necessarily defined. Like
But you need to explain, like, I mean, in the real world, you can pick whatever you want as a pivot, right? And there's good cases and bad cases, right? Like the best ideal case would be to pick the median.
Yeah.
But finding the median requires to sort the list, which
Yeah.
defeats the purpose of it. So, yeah,
like it can be random between the last element or the first element.
yeah.
That's a good choice.
Well, technically speaking, just the last or first element is a random choice because the number there will be different each time.
Yeah.
Although picking the first element is dangerous because it risks the fact that you may get a sorted list, and then bad things happen. So, anyways, question 22 is when you get to the real part of the test. That's going to be the recurrence relation one. But here's the other part. I like this question. So this one's 400 points. You need to, if you don't answer it or if you get it wrong, then you don't get 400 points, right? But if you get it right and you get it perfectly right, you get an additional 10% extra credit.
So 350.
Yeah, 350 points. So what I'm saying is, if you get the question partially right, then you get, I don't know, 350 points out of 400 or whatever. So, you know, it's only worth 400. But if you get it perfectly right, not only do you get your 400 points, but you get an additional 350
I
points.
think no one's gonna get it perfectly right.
Maybe.
So is it gonna be like extremely hard in that case, or like did you pick like?
It's kind of like that worksheet question where you had to analyze the binary search algorithm, come up with the recurrence relation, and then solve the recurrence relation. So it's a multi-step question. So like if you get part of it right, you know, if you mess up, if you come up with the wrong recurrence relation, then solve that, you get partial credit. But if you get the right recurrence relation and then you solve it right, then you're gonna get extra credit. So yeah.
So this is the last problem in the first worksheet you're talking about, right?
I think so. I think so. All right. So then question 23 is another recurrence relation. That one I just give you the recurrence relation. You got to solve it. I don't know if the mustard theorem applies. That's up to you to decide. You do have to provide a little certificate at the end, just to make sure you remember certificates.
Yeah.
Question 24 is another recurrence relation that you have to do.
We have to get certificates for our answers.
Just for the big question, so that's for 22, and then also for 23. 24, you don't have to do a certificate.
22, the big one. So you have.
Yeah, you got to do the full 9 yards for that one. If you want the extra credit, that is. And if you want to get your full 400 points.
Is there a good way?
So all three of them need certificates then, or just?
No, only two out of the three. Yeah, the hard one, the one after the hard one, and not the but not the last one, not 24. So that's the 400 points, 150 and 150. And that brings us to the end of the test. And so that's question 25 is your average typical extra credit question that I give, which you can earn up to 10% if you do everything. The distribution of that is 4-2-4, meaning that there's technically 3 extra credit questions. The first one's worth 4%, second one's worth 2%, the third one is worth 4% for a total of 10%. Bless you. Question 1 of the 3 is something that we talked about in class, and you either know it or you don't. Question 2 is based on the assignment that we did. It's based on the homework. That one I expect most people to get. That's the easy one, but it's only 2%. And then 3 is hard, but I mentioned it might be on a test, so let's see. So you could potentially get 120% on the test. That's the goal. Potentially. And there's no curve on the test, so you know, do your best. Okay, so now we have 2 minutes left. Questions?
So 22 is the only one we actually have to figure out what is the recurrence relation from a given like either
Piece of code, yes.
Whereas the other two are
You're given the recurrence relation. So you're given like a T of n. And remember, if you don't get a base case, you can just assume it's base T of 1 equals 1.
So is there a good way to figure out what is a recurrence relation of a piece of code?
Not really, other than analyzing the code. I mean, convert it into a recursive function
Because like
first.
binary searches, you know, we keep splitting it
Well,
in half.
yeah, but that's easy to see because it's recursive. So I guess one of the ways to do it is to try to convert it into recursive code. If the iterative code doesn't make much sense.
Like,
But there's no barrier. I can't tell you like, yeah, there's a cookie cutter way.
Because like,
There's
how
not.
would you do a recursive relation if you're just like, say it's just a for loop and it's t of n.
Oh, well then that's just n t of n is equal to t of n minus 1. That's it.
T then equals t of n.
Yeah. Plus 1 maybe from overhead.
Is assignment 5 due on Monday? Because I thought you said it was due on Sunday.
It's due whatever Canvas says it's due, so just go with that.
Okay.
Because ultimately Canvas is shuts down once it's due. So. Other questions?
Trying to figure out the base case, right? Like how do you count the what's due on Monday?
I can't hear you. Guys.
What is like the number? So the number of operations is how much what the base case is, right? The number of operations is once.
The base case is going to be the one case where you know what the answer is. So if you know that a list of size 1 takes 1 time, then that's going to be your base case. That's really what it means.
So what are we counting? Are we counting like every like operation?
Every operation that's related to the variable that you're doing the time analysis of,
Okay.
which would be in this case most likely n. Because like, I mean, if you have a function that takes n and you're trying to find out the recurrence relation of like a, which is unrelated to n, that's just constant time probably, because there's nothing happening in relation to the variable. So I mean, we didn't really say it most of the time here, but it matters what you're analyzing it as a base of. But more than likely in this case, it's going to be whatever your parameter is in your function. So your n. Okay? I will upload the recording tonight. So good luck on the test. I will not be here, so today are my last office hours if you want to see me before the test. All right, like and subscribe.